All right, this is Periodic Trends Part 2. We are continuing what we've been talking about, but we're going to talk specifically about the different types of periodic trends, starting out with atomic radius and the definition of it. It's the total distance from an atom's nucleus to the outermost electron, the outermost orbital of electrons. The ionic radius is almost the same thing, but instead of talking about the total distance from an atom's nucleus, we're talking about an ion. Okay, so this is our main difference is atom or ion. Really, it's the only difference. Keep in mind that we're going to go into more detail about the difference between the atomic radius and ionic radius in the future, down in subsequent pages. But on this page, I want you to just focus on the trend if we're talking about an atom or if we're talking about an ion. And we're only, with this trend, we're only comparing positive ion and positive ion or negative ion and negative ion. Here's what the trend is. The smallest atom or ion, in both cases, is the same. The smallest radius, which is like from the center to the outside, it's like the radius of a circle. The smallest is top right. The largest is bottom left. This is the one, the radius is the one that we call a snowman trend. The reason we call it a snowman trend is because just like a snowman, it increases in size as you go down. And if we were to push this snowman over, he'd look like this, right? Look like this snowman, and he's laying on his side. He's decreasing in size as you go from left to right. Another way of looking at this is the atomic or ionic radius, both of them, increase going that way. Let's look at ionization energy. Ionization energy, by definition, is the energy required to remove an electron from an atom in a gaseous phase. I want you to focus on that part. It's the energy required to remove an electron. They do measure it in the gaseous state of matter. And this is a snow cone trend. That's the opposite of a snowman trend because it decreases going down and it increases going across, or we could look at our arrow, it goes like that. Okay, this, by the way, is the same trend for ionization energy, electron affinity, and electronegativity, with some small differences and definitely different definitions. So we'll go through each one. Okay, here's what I want you to think about when we talk about ionization energy. Think, how strong is the nucleus holding on to the valence electrons? How tightly is it holding on to it? How strong is that attraction? With metals, well, metals have a weak hold on their electrons. They don't hold on very tight. They give them away very easily. So they have a low ionization energy. It doesn't take much energy to take one away. Non-metals hold on very tightly. They have a strong hold on their electrons. So they have a high ionization energy. And that makes sense from this trend that we just drew. Electron affinity is slightly different. Same general concept, but it's a little different because it is the energy released instead of the energy required to add an electron instead of remove an electron. So it's kind of the opposite. It's the energy that's released when an atom gets an extra electron, when a neutral atom gets an extra electron. And it follows the same trend. What you need to think about is how easy is it for the neutral atom to add an electron. If it's very easy to add an electron, that means there's going to be a greater amount of energy released, which means that our electron affinity, or EA, our electron affinity, is high, or the higher, greater the electron affinity. If it is hard to add an electron, that means it's going to release less energy when we add the electron. That gives us a lower electron affinity. Okay, again, looking at our trend here, for ionization energy, electron affinity, and electronegativity, the smallest electronegativity, electron affinity, and so on is going to be at the bottom left, and the largest will be at the top right. We're not talking about size anymore. We're just talking about the intensity of this trend. The highest ionization energy is top right, the highest electron affinity is top right, and the highest electronegativity is also top right. Okay, so going through talking about metals now, metals or nonmetals. Metals tend to lose electrons, so it is hard to add an electron. So it means it's going to have a low electron affinity. It doesn't have much affinity to electrons. Nonmetals tend to gain electrons, so it is easy to add an electron. So that means it's going to have a high electron affinity and release more energy when it gains an electron. It's more favorable. Noble gases do not lose or gain electrons, so it's going to be hard to add an electron. We're going to say that it has a high, not high. It's hard to give it an electron, so it's going to have a low electron affinity. Electronegativity is the ability of an atom in a molecule, so in a bond, to attract shared electrons to itself. This happens in covalent bonds, so we're usually looking at nonmetals. But we can be looking at metals as well. Electrons shared by atoms are valence electrons. So we need to be looking at the trends with relationship to valence electrons. Which elements want to attract electrons? That's what you want to think about. Which elements want to attract electrons? Metals have a weak attraction for electrons. So they have a very low electronegativity. Nonmetals have a strong attraction for electrons. So they have a high electronegativity. That's why they tend to either form negative ions or covalent compounds. Noble gases have an electronegativity of 0 because they do not bond. With very few exceptions. So the most electronegative element wouldn't be helium, even though that's top right. The most electronegative element would be fluorine, or F. All right, continuing on, going down a group from top to bottom. We want to explain each of these trends, putting page 1 and page 2 together. The atomic radius, as we go down a group, the atomic radius increases. We've already said that it increases. We said that the ionic radius, as we go from top to bottom, also increases. Remember, radius, both of our radius trends are snowman trends. Then we get our 3 snow cone trends. The ionization energy, as you go down a group, the ionization energy decreases. The electron affinity decreases. And the electronegativity decreases. All right, now let's talk about why. So we're putting page 2, we just kind of reviewed page 2 in that part right there. And then the first page talked about why. As we go down a group, so we're going down a group, the number of energy levels increases. the valence electrons, so that's the outer electrons, when we go out to a new energy level, we went down a group, that means we increase the number of energy levels, so the valence electrons experience more shielding from the core electrons. More shielding means weaker attraction between the nucleus and the valence electrons. So if you have more shielding, you've got weaker attraction between the nucleus and the valence electrons. We've got a greater distance between the valence electrons and the nucleus. The weaker attraction is going to increase the atomic radius. So if you look, we're kind of building a column here, right? That column is just explaining the atomic radius trend. And it's very similar to the ionic radius. The weaker the attraction, increases the ionic radius and the atomic radius. So let's think about that just this time. Okay, we have a weaker attraction, so the electrons on the outside are not being pulled in as closely. If they're attracted less, they're going to be allowed to spread out a little bit more, which makes the radius grow. It makes the atom bigger. Ionization energy is the energy it takes to remove an electron. It's how hard it is to take an electron away, or how tightly the atom is holding on to its electrons. And the other trends are very similar to that. So the weaker attraction, because we went down a group and we've got more shielding, more distance, the weaker attraction decreases the amount of energy needed to remove the electron. It's easier to take an electron away when the attraction's not as strong. The weaker attraction decreases the amount of energy released when gaining an electron. It's not as favorable, it's not as likely for an atom to gain extra electrons if it already has a weak attraction with the electrons it has. And then over here, the weaker attraction decreases the ability to attract shared electrons in a bond. Again, if it already has a weak pull on the electrons it has, when it bonds with another atom, it's not going to be pulling on the other atom's electrons as much as if there was a stronger attraction. So let's go down and look at our trends across the period. Going across the period from left to right, the atomic radius decreases. Snowman trend. Ionic radius is another snowman trend. It also decreases. Talk about why in a second. The ionization energy increases going left to right. The electron affinity increases. And the electronegativity increases. By the way, it is important that you not only know the trends, but also are able to explain why. As we go across a period, so we're going across a period, the number of energy levels going across a period, it stays the same. The valence electrons experience actually the same amount of shielding from the core electrons. But as you go across the period, the number of protons increases. So the valence electrons experience a greater effective nuclear charge. That's the pull from the nucleus. That charge increases, the opposites attract, we have a greater effective nuclear charge, and more protons or greater effective nuclear charge means a stronger attraction between the nucleus and the valence electrons. Now let's look at how that affects each of these: atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity. For instance, atomic radius, the stronger attraction that pulls on those electrons a little bit harder, that decreases the atomic radius because it sucks in the outer layer of electrons closer. All right, we're still talking about radius with the ionic radius, so the stronger attraction decreases the ionic radius. It makes the atom smaller because it's pulling the outer layer of electrons in. Down here, the stronger attraction, once again, does this sound repetitive? It should, but I want you to get in your head, this is how you explain all the trends. The stronger attraction increases the amount of energy needed to remove an electron. Does that make sense? We've got a stronger attraction to the outside electron. If it's a stronger attraction, it's going to take more energy to try to take those electrons away from the atom. And then we're looking at electron affinity next. The stronger attraction increases the amount of energy released when gaining an electron. It's pulling in with a stronger pull from the nucleus to electrons, including electrons that don't already belong to the atom. So when it gets a new electron, it releases more energy. Okay, and that stronger attraction also increases the ability and the tendency to attract shared electrons in a bond, which is what electronegativity is. Okay, that kind of sums up the trends of explaining not only what the trend is, but why. Now we want to go down and summarize it on this page very briefly. All right, so we can write down here, say, as I go down a group, so you can see our periodic tables drawn sideways. As I go down a group, the atomic radius and ionic radius both increase. So both of those increase. The ionization energy and the electronegativity, we could also say the electron affinity, decrease as we go down a group. And the reasoning is right here. The number of energy levels going down a group increase. The shielding from core electrons increase. And the attractive force decreases. Because we have more energy levels, that's actually going to cause a weaker attraction to the nucleus because you've got more shielding and a greater distance from the nucleus. I'm going to zoom out a little bit to do this next part. The atomic radius and the ionic radius, again, are going to follow the same basic trend. And then the electronegativity and ionization energy and whatnot, those follow the same trend as well. Atomic radius and ionic radius, as we go across from left to right, those trends decrease. Ionization energy and electronegativity increase. Our reasoning is because the number of energy levels going across a period stays the same, so the shielding from the core electrons stays the same. We can't use either of those to explain any differences, so we look at the number of protons. The number of protons and the effective nuclear charge as a result both increase, and therefore the attractive force also increases. And that is just kind of a summary of all of the things that we've talked about in periodic trends all in one spot. That's it for this video. The next one is going to be example problems.